Okay, today we're going to talk about conditional probability. And what is conditional probability? It is a probability that one event happens given that another event is known to have already occurred. It is written P, and then you have parentheses and A, and then the symbol is for given is literally just a straight line. It is read the probability of A given B, and B has already occurred. Okay, so what are some properties of conditional probability? First of all, it is not commutative, meaning that the probability of A given B does not equal the probability of B given A. They are two different things. And with two-way tables, the way you're going to figure out or compute the conditional probabilities is to cover up the columns or rows to focus on the conditional part. And we'll be doing some examples like that. In a tree diagram, the conditional probability is given in all the branches except for the first one. So the conditional probability is given in all the branches except the first. Okay, so let's do an example here. Free tacos. So first we're going to summarize the data in a two-way table just to kind of talk about it, and we'll do some conditional probabilities here. So the two-way table, I'll put it over here. We need to give it a heading. And what data we're collecting is winning and free tacos. Okay, so we're going to have column headers of taco, and this would be winning tacos or getting free tacos. And let's say not getting free tacos. And then we also need win and then not win. And then we'll need some totals here. And here. And just a reminder, anything in the, basically anything in the column totals here and here, or the row totals here and here are marginal cell counts or marginal frequencies. So let's read this scenario here. In 2012, fans at Arizona Diamondbacks home games would win 3 free tacos from Taco Bell if the Diamondbacks scored 6 or more runs. In the 2012 season, the Diamondbacks won 41 of their 81 home games. So let's put that information in here. So they won 41. And that means out of 81, that means they must have lost 40. And gave away free tacos in 30 of their 81 home games. So they gave away free tacos in 30. Okay, and that means they didn't give away tacos in 51 of their home games. All right, so continuing on. In 26 of the games, the Diamondbacks won and gave away free tacos. So this would be the joint cell count right here of 26, where they won and gave away free tacos. So pretty much we can fill everything else in. That means 15 of the times they won, they did not give away free tacos. 4 of the times they gave away free tacos, they did not win. And then 36 of all 81 games, they didn't win and they didn't give away free tacos. So we did part A. Now find the probability of winning or a free taco. So this is the formula we learned yesterday. So we need the probability of winning, which is going to be 30 out of 81. And I'm going to put 81 in the denominator here because all of them would go over 81 eventually. So, or winning a taco, we're getting free tacos, which is going to be 30 So these are the times that they got free taco. No, I already did that one. And then I need, winning is 41, sorry guys. So 41 here, 30 here. But I also have to subtract out the overlap, which is 26. Because the 41 along this row where they won, and the 30 along this column where they got free tacos, we double counted this 26. So that's another way to look at that. So I'm going to get approximately 0.56. Okay, what is the probability of winning given free tacos were given out? So I need to look at the focus on the given, which is the taco column, and I want to know of those in the taco column how many won. So it's going to be 26 over 30, which is going to be approximately 0.87. And then the probability of getting free tacos given that you won. So now I'm going to focus on the winning row. And it's going to be those tacos given away. There were 26 out of 41 of those occurrences. So 0.63. All right. So how can you tell if two events are independent? You would probably imagine by looking at this that these are not independent events. Knowing that you won, you're more likely to get free tacos, and it's all about the fact that you scored 6 or more runs when you get free tacos. So that's the driving force there. So how can you tell if two events are independent? There are two tests for independence. And you just use whichever one is easiest with the given information. So the first is the probability of A given B has occurred. Does it equal the probability of A? In other words, knowing that B has occurred does not change the probability for A to occur. And you can do it the other way as well. Probability of B given A, does that equal the probability of B? You do not have to do both of these, okay? Once you prove it, that's sufficient, okay? So just do either the probability of A given B or the probability of B given A to test this. The second one is the probability of A and B, does that equal, and I should put question marks about both of these, does that equal to the probability of A times the probability of B? If they are independent, then yes, it should equal. So let me kind of summarize that. If yes, it means independence of the two events. Or, if you want to think of it this way, equality implies independence. So students sometimes have a hard time remembering, well, am I looking for these two things to be equal or not? Well, if they are equal, it means that they are independent. I see that best in this first test. It's easier for me to see it here, probably you as well. So just kind of make sure you understand how to use those. Okay, so let's do the next question here. It says, are the events taco, winning tacos, or getting free tacos and winning independent? So let's look at that. And I can use either of the two tests. I'm going to use the probability. Let me write that there. I'm going to use the probability to win and see if that equals the probability to win given free tacos were given out. Okay, so the probability to win was 41 out of 81. Y'all make sure you know where I'm getting that from. And then the probability to win given free tacos were given out is 26 over 30. And when I simplify this down, I get 0.51, and that does not equal 0.86. So the events are not independent. In fact, the likelihood to win, given that free tacos were given out goes up. In other words, what this is saying here is it's really saying if free tacos were given out, more than 6 runs were scored. So the probability to win increases. So in fact, the likelihood to win increases when free tacos have been given out. And really, we could replace when free tacos have been given out with 6 or more runs have been scored. Because that's really the driving force behind that. Okay, so that's the test for independence. What is the general multiplication rule? You actually already know this. You probably just do not know it by this term. The probability for A and B to occur is the probability of A times the probability of B given that A has occurred. All right, so I'll kind of show you what this means. In a tree diagram, you can see this. So you would start with the probability of A, and then the next branch is going to basically say the probability for B to occur given that A has already occurred because you're traveling down this branch. And then the other outcome would be the probability for B to not occur given that A has already occurred. So this is the first branch, and of course we could also have another branch down here for something else. So the second branch right here is what's conditional. I'm going to erase that. The second branch is conditional here. Okay, is this on the formula sheet? No, not really. I'm going to show you how you're going to remember this though. There is something on the formula sheet that looks like this. The probability of A given B equals the probability of A and B divided by the probability of B. This is actually our conditional probability formula. So how does this relate? It relates in the manner that if I were solving for A and B right here, I would just cross multiply. So I'll just show you what that would look like. So I would basically do probability of B here, cancel, cancel, and then I would have probability of B here. So it's a probability of B times the probability of A given that B has already occurred. Now this is kind of reversed, but you can see the similarities. The probability of A times the probability of B given that A occurred. So you can, if you multiply along this path, you can see probability of A times the probability of B given that A has already occurred. All right, so when should we use a tree diagram instead of a two-way table? And there are definitely times when it is more useful. You want to use a tree diagram when you are given conditional probabilities instead of joint probabilities. Joint probabilities are easier to put into a table. So you would want to use a two-way table when given your joint probabilities. And joint probability just means when two things are occurring at the same time. Okay, so probability of A given B versus the probability of A and B. So this is conditional, and this would be for a tree diagram, and this is joint, and this would be usually better served with a table. However, could you do either one for either type? Yes, it might just be a little bit harder to get to the conditional probabilities from a table. It might also be a little bit harder to get to the joint probabilities from a tree. All right, moving along. Okay, we're going to do an example here together. So in January, the Kaiser Family Foundation released a study about the influence of media in the lives of young people ages 8 to 18. In the study, 17% of the youth were classified as light media users, 62% were classified as moderate media users, and 21% were classified as heavy media users. So those are just probabilities. So it's basically the population's being broken into different categories. Of the light users who responded, 74% described their grades as good. So that's a conditional probability. While only 68% of moderate users and 52% of heavy users describe their grades as good. According to this study, what percent of young people ages 8 to 18 describe their grades as good? Now, to answer this question, we have to figure out all three ways that people would describe their grades as good. So a tree diagram lends itself very nicely to this. So this will be our plan. If we choose a subject in the study at random, the probability to be a light user is 0.17. The probability to be a moderate user is 0.62. A heavy user is 0.21. Now, the probability for good grades given a light user are 74.74. And then to be the probability for good grades given a moderate user is going to be 0.68, so it goes down a little bit, and then finally 0.52. So there seems to be some sort of relationship here. So let's write this out. So I have my students in the study. They are 8 to 18 years old. And I'm first going to break apart just the probability for light and moderate. And then heavy. And this would be users or usage. Okay, let's put some probabilities here. 0.17. 0.62, and 0.21. Then, if you're a light user, I'm just going to say good grades, bad grades. Well, let's just say not good. And then same thing here, good, not good, good, and not good. And these are all conditional probabilities. So if someone said they were a light user, they reported the probability, given that they were light users, to have good grades is 0.74. So this would be 0.26, 0.68, meaning this would be 0.32. Here we have 0.52. And here we have 0.48. Now, I want to show you something. If you multiply along the paths here, so if you multiply along the branches, this would be a light user who said they had good grades. If I multiply along the second path, it's a light user who said they don't have good grades. So these are our probabilities. So the first one is the probability for light usage and good grades. And that's when you would multiply along the path like this times 0.74, and I get 0.1258. Okay, so probability light and not good is going to be 0.17 times 0.26, and that's going to give us 0.0442. Okay, so I'm going to pause the video now, and I want you to actually fill this in, and we'll check back in just. Okay, so check all your probabilities, and if you were to add all of these probabilities up, you should get roughly 1. It might not be exactly 1 due to round-off error, and the 3 that I'm looking for all involve good grade. So it'd be this value, and this value added together. So I'd have to add all those together. So let's kind of conclude. So the probability to have good grades would be when you add 0.1258, those are the light users, and then 0.4216 and 1092, and it is 0.6566. So we can conclude about 66% of the students in the student body or the study describe their grades as good. All right, so let's continue on. Okay, what is the multiplication rule for independent events? The probability of A given B is equal to the probability of A times the probability of B. And then this is for independent events. Is it on the formula sheet? No, it's just something we're going to have to memorize. How is it related to the general multiplication rule? So let me remind you of what that is. The probability of A and B equals the probability of A times the probability of B given A. And you can see they're very similar. This is for independent events, and this is for not independent events. And the thing to notice, if I were to use this second formula, the general multiplication rule, this second part would actually simplify down. If they were independent, it just simplified down the probability of B, so it matched the other formula. So let me kind of just go through that. When events are not independent, the general multiplication rule, this should say independent, sorry about that. The general multiplication rule simplifies, and that's this formula right here. And honestly, you don't ever need to know that that's what this is called. Simplifies to the multiplication rule. This is due to the fact that for independent events, the probability of B given A will equal to the probability of B. So it simplifies down to the same value there. So in other words, you can always use the second formula, but it's just simpler to use the first one, obviously. So what is the difference between mutually exclusive and independent? They are not related. At least not in the way you may think. Most students think mutually exclusive implies independence as actually opposite. So if you have two mutually exclusive events, they can't be independent. And it has to do with the knowledge of the different outcomes. I'll explain what I mean. So say I have a deck of cards and A is going to be a red card and B is going to be a club. These are two events, standard deck of cards, so you kind of know something about the deck of cards. So the probability of A and B occurring is never going to happen. These are totally mutually exclusive, and it's because clubs are black. Now, the probability of A is 0.5 because half of the cards are red, half the cards are black. So the probability of A given B is going to be 0. So knowing that I have a club, the probability to have a red is 0. So that is why mutually exclusive events will never be independent. And I basically just used the test of independence here. So the probability of A does not equal the probability of A given that B occurred. The two events are not independent, but are mutually exclusive. And I'm abbreviating a little bit there. Okay.
Teachers, if you would please look at the rosters.
So sorry, guys. Go ahead, and we're going to do the next 3 examples in class with partners.
The 700 hall.
So that wraps up today.